I forgot. Simon, is it okay to record? Just
Sure.
yeah, sorry, I forgot to ask before. Yeah, so welcome everyone to the Sydney CPPC seminar. Our speaker today is Simon Knapen from Berkeley, Lawrence Berkeley National Lab. Simon did his PhD at Rutgers University in 2014 and then moved on to a postdoc at Berkeley. From there, he moved on to a postdoc at Princeton Institute of Advanced Study, then to CERN, and since 2021, he's a faculty member at Berkeley National Lab. And today he will be telling us about the sound of dark matter. So please, Simon.
Thank you. Yeah, thanks so much for having me. Let me know if you have trouble hearing me, and feel free to speak up on Zoom as well if you have a question. I'm not very good at monitoring the chat in real time, so just interject whenever. Yeah, so I'll be telling you a few things about some of the calculations that I've been doing in the last few years together with Tanya Lin in San Diego and some people in her group, as well as people here at Berkeley, and now recently also Stefania Gori and Pankaj Mundal at Santa Cruz. Okay, so this is just, very quickly to warm up on things. I think all of you are in this audience are very familiar with the sort of landscape of dark matter, right? So usually we plot things just with this x-axis only. We have this very vast range in which the dark matter can live. But I like to at least attempt at some qualitative level to draw the y-axis as well, where there is some sort of coupling, which, given that all these different models have different coupling constants and so forth, you can't really make that quantitative, but sort of at a qualitative level. You see at high masses, we have constraints in the LHC. Down to like an MEV or so, meson factories are pretty important. In particular, K-on decays, K to pi nu, B to pi nu, this kind of constraints. And then once you go below a few keV, astrophysics becomes very important because you start having stellar cooling bounds and that kind of things. And so then you get very strong constraints. So I tried putting some of the sort of traditional dark matter candidates on here. And so, of course, we spent a lot of time looking for axions and looking for WIMPs to live in these respective corners over here. So what I'm going to try to do today is look for some of these, talk about how we can look for some of these things here in the middle here. So there are a few sort of slightly less, I mean, by now they're very well studied, but they're somewhat less predictive in some ways than some of these axion models. But you can still get very nice dark matter candidates out of freeze out or an asymmetric dark matter, strongly interactive particles or freezing candidates. Again, all these blobs are very qualitative. They can move around depending on what you choose. But so we're going to live in this regime between a few keV up to like a GeV and mass. That's sort of the regime that I'm going to target. The reason being that there's a lot of experimental effort here that is ongoing and a lot of cool theory challenges that we need to address to try to make this program a success. And so this will be complementary to the existing dark matter trusts that we have in axions and WIMPs. So here is a sort of an old plot that I took from one of the cosmic fissions workshops from a few years ago. And so you see dark matter mass versus dark matter nucleon cross-section. And so these shaded regions are things that were excluded at the time. By now, the bounds are quite a bit stronger. But sort of on the right-hand side, what we're doing is we're pushing down to the neutrino floor. And the way to do that is to just get more xenon, wait longer, and work really, really, really hard to get those backgrounds as low as possible, and then basically just integrate exposure until you hit the neutrino floor. And so that's necessarily a very time-consuming process because there's only so much xenon that you can consider buying. So on the left-hand side, in order to make progress in this part at lower masses, what you need is lower thresholds for your detector because your dark matter has much less kinetic energy, and so it's going to give much lower energy excitations if it scatters with your detector. And so on the experimental side, the sort of two dominant paradigms in this region are sort of ultra low threshold colorimeters. So you're basically looking for either heat or scintillation photons at very low energies, or CCDs, essentially, skipper CCDs that can look for single electron excitation. So you're trying to excite one or two or three electrons across the band gap and try to see these things. There are sort of a couple more fancier proposals that are coming online now, like things with isomers and so forth, where you try to de-excite an excited nucleus and so forth. But sort of generally speaking, most of the experimental effort has been in these first two categories. So just as maybe a review of sort of the existing direct detection landscape, right? So generally what has been done so far is you can either try to detect dark matter through heat, charge, or scintillation light. And each of these experiments have sort of picked a lane, or in many cases, like two different signals in some ways. And that helps, of course, with discriminating the signal from background if you can measure, for instance, both charge and heat. And so this becomes more and more tenuous when you go to lower and lower thresholds, because, for instance, you might find yourself below the ionization threshold of your material, and then the only thing that you have available is heat. But generally, this next generation of detector is going to build on this existing technology and try to push this to its logical extreme. And the way that is done is with quantum sensor technology. So you're trying to essentially look for individual quanta of charge, or phonons in the case of the heat detectors. So here's an example of an existing detector that has taken a lot of data that is working in this regime. So this is super CDMS. And so what you're looking here at is like a hockey puck size piece of crystal. So this is either silicon or germanium. They have both. It's a semiconductor. And what happens is if a dark matter particle comes in, it scatters, it creates a nuclear recoil. That nuclear recoil travels through this crystal, dissipates a bunch of phonons. And so this crystal is cooled at very low temperature, sub-Kelvin temperatures, which means that these phonons can travel ballistically in this crystal, basically. So they don't get attenuated. So they bounce around, and eventually one of these phonons might hit one of these lines that you see at the top of this of this disk, right? So these are superconducting collection fins. And so when a phonon hits one of these collection fins, what it's going to do is going to break up some Cooper pairs, and that energy then gets transported through this superconducting circuit to what's called a TS sensor, so a transition edge sensor, which is this tiny little thing over here, is a couple of microns in size. And so this gadget is basically a very thin superconducting film that you dial right onto its critical temperature. So it's very, very sensitive. So if you ping it with a little bit small amount of heat, it goes non-superconducting, and you can read out that amplification with a squid, basically, and then extract the signal that way. And so this is a very ingenious method which Super CDMS and other experiments have pioneered to couple a tiny, tiny, very sensitive sensor to a macroscopic volume, basically. The reason why you need to do that is because the energy resolution of your sensor is always proportional to the heat capacity and therefore the volume. So if you want to have a very, very sensitive sensor, it needs to be very, very small, but then it's by itself not a very good dark matter detector because the volume is not large enough. And so this is how Super CDMS solved this problem, by basically using the fact that these phonons can bounce around for a very long time, and you can take your time to collect them and integrate them in this very tiny, very sensitive circuit. So the second thing that they can do is they put a bias voltage on this thing. And so then what happens is any ionization electrons that you make get drifted upwards. And so they create further phonons. And so those phonons again get read out. And this is a way in which they can also look for ionization yield. So that signal is a bit delayed relative to the phonon signal. And so they can separate these things out. So this is something called the Lukneganov effect. So what the next generation of sensors is going to look like, this is work being done, led by Matt Pyle and Dan McKinsey at UC Berkeley. It's called SPICE, and Herald is the helium version, and the sort of consortium of this experiment is called Tesseract. And so the idea is to do essentially the same thing, but shrink the detector down, make the sensors even smaller, even more sensitive, and remove the bias voltage. So again, what happens here is a dark matter particle comes in, it creates one or more phonons. Those phonons tend to undergo some sort of parton shower, so they split into multiple other phonons. until they are soft enough so that they can ballistically travel to the crystal. And eventually they get collected by the superconducting fins over here and drifted to this very tiny sensitive sensor. And so their theoretical limit, which is where they're aiming for, is to get about 10 millieV energy threshold on this. And so right now they have energy thresholds of about 30, 40, 50 millieV, depending on which sensor. And so they're working now on interfacing these tiny sensors with a crystal, which would be about a centimeter cube in size, something like this. So what you're seeing here on the right is like a larger version. So this is a sapphire disk they had laying around. And so they etched each of these dots here is basically one of these blue collection fins with a sensor. So this one has a higher threshold because it's a fairly large detector. So they're not quite down to where the threshold they want to be eventually, but it was sort of a prototype they're working on. So this thing works, has a decent exposure, and has a sub-EV energy resolution. So I've already taken some data with this thing, which they're currently analyzing. Another thing you can do, which is more along the lines of the sort of analog of the xenon experiments, is you can, instead of xenon, you can use liquid helium, which is a superfluid. And so what's nice about that is that you get your nuclear recoil, and because this thing is a superfluid, again, your phonons are going to travel ballistically. So they bounce around, and when they hit the surface, what they will do is what you see here on the bottom right. So the phonon comes in, it's going to like evaporate a helium atom. That costs about 1 millieV worth of energy. So some phonons can do that. And once this helium atom drifts upward, there is again this sort of sensor over here. It sticks to this sensor and gets a couple tens of millieV of binding energy because there's a van der Waals force here. So you get a little bit of an amplification here. And so this is how they're hoping to advance this concept for superfluid helium as well. But sort of the basic concept is that the phonons travel long distances before they dissipate, basically, and you can try to read them out before you thermalize with your target material.
Can I just ask a question about that step?
Yeah.
Is that really the only way that you're going to evaporate a helium atom from the surface? What else do you have to do to prevent that from happening?
Well, this fluid is extremely cold, right? So they do this at the helium one, I think at around 100 millikelvin, if I remember correctly. So there are no more phonons in this. You know, all the phonons of the terminal phonons are fully frozen out, right? So anything that is evaporating a helium atom was some external perturbation that entered your detector.
Right? So you have to stop radiation from hitting it, for example.
Yes, of course. Yeah. So you have to do the same backward mitigation strategies that you do for a normal dark matter detector, right? Like, you know, you're building an extremely sensitive sensor.
Yep.
And so the downside of that is that it is an extremely sensitive sensor to anything, right? And so
no, I'm just thinking round through the interface, because with the earlier example, when you've got the phonon rattling around in the superconducting body, that was sort of a more obvious example. This just sort of trying to think, okay.
Yeah, no, this is a bit, this actually has been demonstrated that this works, right? So you can excite helium or for instance, with like optical light, and then try to like read out those phonons. So they have taken data here. Yeah, whether or not the backgrounds can be fully mitigated is something that's, of course, the hardest part, and they're working on that. Yeah. So there's an amusing technical challenge associated with this detector is the fact that helium likes to crawl up to the walls, right? And so
this is the other thing that I was just sort of trying to think through. Do you not have to?
Because you do have to worry about it. Yeah, it's very annoying. So it tries to crawl up the walls and then stick to the sensor, and then the sensor is useless.
Right.
And so what they need to do is they need to deposit in situ some cesium powder near the edges of the surface. So for whatever reason, helium doesn't like cesium. And so, but you only can do it after you vacuum seal the detector. So there's some very elaborate system they have in place to deposit cesium after the fact.
Because you don't only have to worry about helium being liberated from the surface, you have to worry about helium that's creeping up the sides of the thing being liberated from that surface, which presumably has different properties, and
Correct. Yeah. So this is really an R&D effort that is, yeah, they have ideas on how they've been fairly successful in addressing that, but it is challenging, yes. And so apparently cesium is the answer.
Okay.
At least that's what they think. But yeah, yeah, this is a very interesting system. It's very complicated, but potentially it has a lot of potential because this is much more scalable than your little cube of sapphire or gallium arsenide.
Sure. And I mean, the amplification here is nice. I mean, that's
yeah, the amplification is quite nice. Downside is the sound speed is rather low, so the phonons are fairly soft relative to a crystal.
okay.
So a trade-off there. Yeah.
All right. Thank you.
Good. Yeah, those excellent questions. Yes, thanks. Okay, cool. So there are also electron detectors, so like Skipper CCDs. And so here the idea is that you measure the same CCD cell multiple times, basically. And so what they do is they sacrifice timing by doing that, but in return, they get this really, really nice charge separation. So they can really separate individual, count how many electrons were deposited, liberated in this, in one sort of cell. So they have already quite a bit of data. Sensei is the main collaboration here. Damek is using the same technology. And so they have about 50 gram days exposure. And Minos now, I think they recently started taking data in a more deep mine. I forgot which one, but it was probably Snow. Okay, so now I'm a theorist, right? And so the question is, okay, what do we need to do on the theory side? Because, this is cool experimental stuff, but we want to try to contribute something. So there are a couple things that we need, right? On the one hand, we need to worry about models, right? Because once you go down to sort of low mass region, especially for the higher cross sections, you need to build a full model and check that it's not already ruled out by, stellar cooling bounds, collider constraints, and so forth, because there's going to be some mediator particle. And that mediator particle itself has constraints on it. And so this is something that we sorted out a number of years ago. So we think we understand what lives in this space. The second thing, which is I think in my mind more interesting, is we need to do dedicated rate calculations here because your dark matter wavelength is long enough now that you no longer do elastic recoils. You have to do more complicated things, as we'll see in a moment. And then finally, we're working on trying to help with background predictions for these experiments, try to help them understand what background events they're seeing and how they can try to help mitigate them. So I'm going to mostly talk about two, and then time permitting, I will talk a little bit about some of the background predictions that we've been working on. So here's a bit of a cartoon to just give you the sort of length scales, right? So in the sort of mass range from keV to the Planck scale, the momentum transfer that's happening in the process is always just the dark matter velocity times the reduced mass of the dark matter with the object that it's scattering with. And so if you have GeV and above, it means you have a momentum transfer of the order of an MeV to 100 MeV. So that's 10 to the minus 2 angstrom and smaller, which is basically nuclear recoils. You don't really see the interior of the nucleus, except for some special cases. But you also don't really see anything else. So you can really treat the nucleus. Once you have the form factor, you can do elastic scattering, which is what's been done for decades now for the regular direct detection experiments. Once you go down in momentum transfer, you keep going up in the Broglie wavelength, basically. And you start being sensitive to electronic structures, right? This is very important for something like Sensei, where you really need to understand the wave functions of the electrons in order to accurately calculate whether or not an electron gets liberated when it scatters with the dark matter and promoted from the valence band into the conduction band. And then at very long wavelengths, what ends up happening is your wavelength is so long that it sees multiple lattice cells at the same time, and you can no longer scatter in a single nucleus. You have to instead scatter with phonons directly. And so what we need to do is we need to transition to a new effective theory where we effectively integrate out the atoms, and we match onto an EFT where there's a phonon dark matter coupling, and we can calculate in that theory. So we've been working on both of these aspects, on the electronic stuff as well as on the phonons. But for today, we're going to be talking about phonons. And then if you want to hear more about electrons, we can discuss after the talk. So these are the materials that are most interesting. So they're called polar materials because they have two atoms in the unit cell. So in this instance on the left, this is sort of the simplest one, is a cubic crystal called gallium arsenide. So there's one gallium and one arsenic atom here in green. The one on the right is sapphire. It's a more complicated beast. So a unit cell has 10 atoms in it. So there's 4 aluminum. So this one, this one, this one, and this one. By the way, can you see my cursor, or otherwise this will be very hard. And then there's a crown.
Yes, we can see it.
Okay, good, thank you. And there's a crown of 3 oxygen atoms here. So it's basically an elongated sort of cell. So there's a primary crystal axis. So first, let's start. I'll explain in a moment why we care about these polar materials. But first, let me just take a step back and talk a bit about phonons and how do we deal with these things, right? So phonons are basically just a very complicated system of a couple of harmonic oscillators, right? So you can think of this sort of cartoon of a 2D crystal. So each atom has some equilibrium position and then a displacement vector u around its equilibrium. And basically, you can think of this system as just a bunch of springs connected with each other. So if you can calculate what the spring constants are, you can diagonalize the system, find the eigenfrequencies and the eigenmodes, and you have all you really need. And you can treat these phonons as a set of harmonic oscillators. And so this is how you do this numerically. So like there are these density functional theory codes that you give it a crystal structure basically, and what it can do, it can calculate those force constants for you. So this runs on a supercomputer over the weekend, depending on which material that you're interested in. And then once you have those force constants, there's a separate piece of code called phonopi that diagonalizes that thing for you. And that gets you eigenfrequencies and eigenvectors. And so you see for gallium arsenide and sapphire, you see this in these 2 plots. So let me walk you through this. So on the x-axis with these very funny symbols, gamma, x, w, and whatnot, this is the momentum vector, where these represent points in the first Brillouin zone of the crystal. So gamma is always the origin, so this is 0 momentum. And then X and W and L are some points on the edge of the Brillouin zone. So these are finite momenta, roughly like a keV each. And so this represents different directions in the crystal that you can look at. So you see that gallium arsenide has 6 phonon modes, which is very logical since it has 2 atoms in the unit cell with each 3 degrees of freedom, total of 6 degrees of freedom. So you expect 6 eigenmodes. So 3 of them are acoustic modes, 1 longitudinal and 2 transverse modes. These things you can loosely speaking think of as the Goldstone bosons of the fact that you broke the translation symmetry in this crystal by putting down a bunch of atoms. And so they have no energy at 0 momentum because they are derivatively, they have a derivative dispersion relation. The optical modes are the modes where the 2 atoms are oscillating in antiphase with each other. So they're the equivalent of the standing wave. So that means that even if they don't propagate at 0 momentum, they can still store energy. So that's why they are gapped, right? And again, you have a longitudinal one and then 2 transverse modes. Sapphire, same thing. There are 3 acoustic modes and then 27 optical modes. And there's just more of them because the unit cell is more complicated, but the physics is identical. It's exactly the same. It's just a more complicated system, but other than that, these are just all optical modes where things are just moving in antiphase with each other.
So I have a question here. So what?
Yes.
So what if you have defects in the crystal? Are those captured in the calculation? Like, okay,
Good.
impurities you might be able to actually do better with if you put in impurities and things like that. But if you have structural defects or something.
Yes, so these don't have any defects in them, right? Because this is, in the end, the crystal that is used here is an 8 by 8 by 8 crystal with periodic boundary conditions. That's how you calculate, do this density functional theory calculation. So what impurities will do for you is they won't really affect, assuming that they're not abundant, right? That they're small and their abundance is small enough so that the crystal overall is still a regular lattice, not like a glass or something like that. They won't really affect this dispersion relation, but what they will do is they will affect the lifetime of these phonons. So some of these phonons, they can hit an impurity and then down convert to softer phonons.
I see.
So that's one effect that these impurities can have. So you don't want to have too many of these because then, you know, that makes the phonons down convert faster and becomes more and more difficult to recompile. So you want a reasonably pure crystal. However, the purities that they are fabricated sort of on an industrial level are more than sufficient for this purpose. As we will see, hopefully at the end of the talk, impurities can be difficult because they can be a source of phonons and they can be a source of backgrounds rather than sort of, so that is a potential problem that they have to deal with.
Thanks.
Yeah, very good question. Okay. Good. So here's maybe just to make this whole thing a little bit more visual, right? So this is an optical phonon. So I have a gallium atom and an arsenic atom. And so these things are oscillating in antiphase. And so now this is why I need the polar material. So polar material means that the charge of each of the individual atoms is slightly different from each other. So the electrons are dragged more towards one side. And so that means that some dark matter particle comes in with a tiny electric charge. What it will do is it will pull one atom the other side and the other atom the other side, and it excites this optical phonon. And so this is, if you have a dark photon mediator, for instance, this is exactly what it's going to want to do. It's going to try to excite these optical phonons. And that's nice for us because those are the ones that are the highest energy and they're the easiest to see. The way you can see this is the Hamiltonian of a dipole P in Fourier space, seeing some test charge with charge E prime here. This is just a Fourier decomposition. In a lattice, it's essentially the same thing. It becomes a little bit more complicated because there's a reciprocal lattice. There is this epsilon omega tensor takes into account the screening from the electrons. And there's an effective charge of the ions, which you can calculate. And this is the polarization tensor of each individual phonon node indexed by mu. And then we quantize this thing, so you get a creation operator here, as well as the usual normalization of the harmonic oscillator, which involves the energy of the thing that's oscillating, which is the phonon frequency here. And so this thing has been around since the 50s. So this is the Froehlich Hamiltonian. And so it's used to understand how electrons interact with phonons in semiconductors. So as long as we understand what these omegas, these z's, and these e's are, which we can get from these calculations I described earlier, we can do quantum mechanics for this thing, and we can calculate the rate at which dark matter produces an individual phonon, a longitudinal phonon in this instance. Now, let's try to do this a little bit more systematically, right? So this is just one example for one phonon only. And so for that, we want to sort of understand the parametric scaling of this dark matter phonon effective field theory. And so first, I want to remind you, there's a nuclear recoil where it's just a single nucleus recoiling. You need to put the nucleus on shell, of course, in the initial final state. And that means that the energy that's transferred in this process for a nucleus at rest is given by the square of the momentum transfer divided by the mass of the nucleus, right? So there's the usual dark matter direct detection kinematics. So the phonon regime is characterized by the limit where the momentum transfer is very, very small compared to the square root of the energy and the mass of the thing that's recoiling. And so what we're going to do is we're going to have a momentum expansion in this order parameter Q over here. Order by order in perturbation theory, basically. That's how this theory is organized. And so very, very loosely speaking, you can think of some of these phonons as goldstones. And so this sort of derivative scaling, if you want, is maybe not so surprising from that point of view. Of course, there are very important caveats and so forth. So it's not really a hard statement, but just to gain some intuition, it's somewhat similar to chiral perturbation theory. And so I already mentioned that we learned a long time ago how to do this at leading order, right? I described it for one specific model, but you can do this for all sorts of models, scalar mediator, dark photon mediator, as well as other things. And we can derive how this scales at the leading order in momentum transfer. And so depending which model you're looking at, you might be exciting some of these high energy modes or some of these low energy modes. Now there's an issue with this. Before I do that, here I actually wanted to show you this is the most dominant optical mode in sapphire. So again, I promised there are 4 sapphire aluminum atoms and 6 oxygen atoms, and so you're oscillating antiphase like this. So this is the main mode that's being excited. Now, so we need. I promise we're going to try to do. Okay, and here is some example of each plot, but This is all very optimistic because no background and so forth. We'll get back to some plots like this in a bit of a moment. Now we want to do this more systematically, right? And so the reason why we need to do that is because if we expand in very small momentum transfer, it means that we're restricted to very low dark matter masses, below 1 MeV. Because as the dark matter mass goes up, this momentum transfer goes up, and you find that your leading order term is no longer good enough. And so this is a project that we did with Peter, I think, who's also here a few years ago, where we calculate the next leading order, where you get this sort of two types of terms. You get a new term from the matching of the EFT, which is this seagull diagram here on the right-hand side, but you also get these sort of inelastic effects. So the phonon self-interactions start mattering. And so we did this calculation, and this is part of the answer. It's a bit of a mess. In the grand scheme of things, it's not as complicated as this might as this looks, because there's just a lot of notation that you need to define. Once you've defined the notation, these are just tree-level calculations, are not that fancy in the grand scheme of things. However, you sacrifice Lorentz invariant because you're doing a relativistic calculation, and things get kind of hairy because you don't have as much symmetries as you have in that you usually have in regular QFT. So this is not really a sustainable path forward. So we can't keep doing this to arbitrary order and get the result that we need that's valid for every dark matter mass. And so recently we figured out how to do this resummation, basically, where we do this to arbitrary order in N and then sum up all the diagrams. And we were able to show, as I'll explain in a moment, that if you then take the momentum to infinity, you recover the nuclear recoil, which is this delta function behavior here, where you force the energy to be this dispersion relation. So let me show you how that works. So there's a few additional approximations that you need to make in order to perform this calculation. So at low momentum, you have these wavelengths that are very long compared to the interparticle spacing. And so the interference between the individual atoms is absolutely critical. And so the sort of basic example that we all know from freshman physics is Bragg diffraction, right? So which really relies on this wavelength being long. You get constructive interference for very specific values of the momentum. Now, if you go higher and higher momenta, where the wavelength becomes of the order or smaller than the interparticle spacing, this interference becomes less and less important because these phases are going to start averaging out. And you can start dropping these terms, and that greatly simplifies the calculation. The second thing that you can do is beyond next leading order, you can start dropping these diagrams over here. And so if there's interest in it, I can explain a little bit more detail.
Sorry, can I ask a question again? Sorry for interrupting.
No worries.
So what does an NLO calculation really mean in this formalism? Because, I mean, we are not doing a relativistic calculation, right? So what does NLO really mean?
Yeah, it means, hopefully it will become a little bit more clear in the next few slides, but it's basically an expansion in the number of final state phonons. That's what it means.
I see. Okay. All right. Okay, that makes sense.
Well, because you should think about it like chiral perturbation theory, where there is some.
Okay. No, that makes sense. Okay. Yep.
Yeah. So like the more legs you add, you go higher and higher order in your chiral.
Yeah. Okay, that makes sense. Okay. Yep.
But no loops are being calculated here, and thankfully.
Yeah. So that was my confusion. Okay, so this is just an expansion in. Okay.
Correct. Yes. And then finally, we're also assuming we're taking an isotropic approximation. This is not actually essential, but it really helps with evaluating the phase space integrals. And so one of the things that we need to do next is to generalize beyond this. The reason why we haven't done it yet is because it probably involves switching to Monte Carlo integration. And so we'll have to write a Monte Carlo generator, which is not technically complicated, but kind of annoying. It will take a bit of time. Okay, so I'm going to try to explain qualitatively how we do this. And so the calculation is actually not that complicated. However, there's a lot of notation that goes into these things. And so I didn't want to bog you down with like introducing all this notation. So I've tried to strip down some of the notation by removing a bunch of indices. And so I'll explain what this is, and hopefully we can get a feel for how this is done without going through all the details. So first, you start with Fermi's golden rule. So your differential cross-section is proportional to this matrix element over here. So phi of f is the final state. Phi 0 is the ground state of the crystal. And then in this instance, I just put in, this is just a contact interaction in real space, which Fourier transform becomes this exponential over here. We squared the matrix, we sum over all the atoms in the crystal, which is this index L. We square it, you sum over all the final states, and then finally you plug in, you add in energy conservation. So this is just Fermi's golden rule, really. So the next thing you can do is you can open up this square, really, right? And just write this as the thing times its complex conjugate. There's a double sum over here. And I Fourier transform this delta function over here. So I get this e to the I f omega t factor on the right-hand side. And so next, since we're summing over all possible final states, this is a complete set of states. So I can remove this bracket in the middle over here. And when I do that, I get this two-point correlation function like this. So here, the additional trick that I did is I brought this number over here, this e to the I omega, e to I f minus omega t phase into one of these correlation functions, and then I can promote this to a Hamiltonian basically, and act on one of these states. And so you get this time evolution operator over here. So you're basically time evolving this, and that's equivalent to the thing over there. So this is somewhat reminiscent to what you'd be doing when you're deriving the optical theorem, where you also again use this complete set of states over here. So if you can calculate this two-point correlation function for arbitrary L, L prime, and arbitrary T, you're done, right? So this is all you really need to compute this cross-section. Now, in general, for a crystal, without making any approximations, this is an extremely complicated object because there are tons of atoms in this crystal. They all interact with each other in various ways, and so forth. Now, it turns out there are two simplifications that you can make. So either you can say, well, okay, I'm going to assume that Q is small, and I can expand these exponentials. And then I get a much simpler object. And so this is what we did when we computed the single phonon rate. So we expanded to leading order in Q, and then we evaluated this two-point correlation function. And then this is how you calculate dark matter scattering into a single phonon. If you want to know the answer to arbitrary phonons, you can't do that. You have to keep this exponential. By the way, so the R here is the displacement of the atom with index L. So you can think of this as containing the individual phonons. So once you go to the basis, you diagonalize the system, you again find creation and relation operators that are sitting in this exponent here that come from this R object. Now, if we're allowed to drop the interference terms, right, if I assume that these phases average to 0 if L and L prime are not equal to each other, and I just keep the case where they're both equal to each other, this correlation function simplifies massively. And so I can again proceed with the calculation without having to do this power expansion here. And so this is what you're seeing over here. So I'm just taking this out here just to simplify things. And it turns out you can do some algebra and write this as, instead of the correlation function of these two exponents, you can use some Hausdorff identities and so forth, and write this as the exponent of this correlation function, plus corrections that are subleading, they're suppressed by the phonon self interactions, right? And so now this is again a somewhat simpler correlation function because I know that these RLs are behaving like harmonic oscillators, and I can analytically calculate what this object is over here. Yeah, and so essentially you basically treat the crystal as a sum of harmonic oscillators that are weighted by the density of states of the phonons, which is something that you can look up in the condensed matter literature. So this is the answer to all orders in the number of phonons. So here the sum over n is the number of phonons, is AD here up front is the atomic number of the crystal, of the atom, sorry, that you're scattering with, and you're summing over all the atoms D here. And there's an object called the Bayer-Waller factor, which is just measuring the delocalization of the atom, but it's not very important. This factor is very close to 1 for most of the space that we're interested in. And so you see here, there's this sort of term by term, I have this sort of closed form expression where all the additional information of the crystal is packaged into this density of states, which you can here see for the example of sapphire. So here you see the acoustic mode, sorry, and at higher energy you see there's some peaks for the optical modes. And I basically have this expression where, again, energy conservation is imposed at the end. Is there any questions about this, or is this very very far off? The details are very hard to follow, but I hope that the qualitative picture is maybe okay. But let me know if there's anything I can clarify.
Can I ask one question to that? So you basically, a few slides earlier, you mentioned that interference is important, and now here you make that assumption that L is equal to L prime.
Correct. So this is now, interference is important at low momenta, right? So the formula that I'm showing you over here is valid at for momenta roughly around a keV and higher. So this is wrong.
It's large momenta. So basically, okay.
Exactly. So at low momentum, you have to match this formula to another formula, not this one. That's a separate calculation. Exactly. Yes. There's no single set of approximations that you can make that is valid everywhere. So you have to do this in pieces and then stitch the two calculations together.
Okay. Thanks.
That's a very good question. Yes, that's very important. Yeah. Okay, so now what happens if we go to higher and higher momentum, right? So I keep cranking up the momentum. You see this thing here at the top. Okay, there is this 1 over n factorial showing up and something like q to the n. So the only reason why this doesn't look like an exponential yet is because of this delta function over here. But if you go higher and higher momentum, this delta function becomes increasingly less important, and you can approximate this formula by this exponential over here. And you can show this explicitly by starting with this full correlation function earlier on that I had, and then do a steepest descent analysis. And then you can directly recover this without computing it order by order, basically. Where this delta object over here is the width of this exponential. And so this is an integral, it's an object that depends on this density of states over here. Its exact shape is not very important. And then if I keep going even higher momentum, eventually this delta is going to become smaller and smaller relative to this numerator over here. And this exponential is going to start asymptoting. This Gaussian is going to start asymptoting to a delta function. And so this is very, very cool because now I recovered explicitly, analytically recovered the free nuclear recoil limit, which is very nice because I have an order expression and it sort of is a nice asymptotic formula which recovers fully what the answer should be in the limit of just a singular nuclear recoil. So in a way, you can think of an individual nucleus recoiling as the infinite phonon limit of the sort of multi-phonon calculation, which is pretty neat.
Sorry, you mentioned this, but I'll ask this again. I think, so what controls the width of the Gaussian?
The width of the Gaussian control is controlled by the momentum.
Oh,
so this is a function of momentum, as well as this density of states over here.
So if my material was, and again, I'm going back to the question of whether there is a defect or not. If my material had other, defects, impurities, whatever, because then I have to rethink how I do my density functional calculation, probably. I don't know, but I'm just...
Yeah, so if you had a huge amount of defects, right? Let's say there was like a defect in every other crystal cell, then this would start affecting the density of states. But in that case, like, you're dealing more with the glass rather than regular lattice.
Okay, yeah.
And so there is a different set of calculational tools that you can use in that case. So like here, I'm still relying on the fact that I have periodic symmetry to a very good approximation.
Okay. All right. Okay. Thanks.
Like if there's a defect every 100 lattice sites or so, I'm not going to be bothered. If it's every few lattice sites, then this would probably be not very good.
Yep. Okay. Thanks.
But there exist calculational techniques in the condensed matter literature that deal with that case as well. So it's something that one could do.
All right. Thanks. Yep.
Cool. So here's what this looks like numerically, right? So this is the differential scattering rate in some arbitrary units that you shouldn't get too distracted by as a function of momentum and energy for 3 different momentum slices. So low momentum on the left, medium momentum on the right, and high momentum on the, medium momentum in the middle and high momentum on the right. with energy on the x-axis. So at low momentum transfer, you see individual phonons. These are various spikes that you see. So you're basically resonantly exciting one phonon at a time. Once you start cranking up the momentum, you start seeing these sort of multi-phonon, two phonons start becoming important, a little bit of three phonons. So the different colors here in the legend are the number of phonons that are being produced. So the orange is two phonons. So here the single phonon still dominates, but two phonons start to creep in, three phonons, four phonons. If you go to very high momentum, you see all these terms start contributing equally, right? And this is just some evidence that this power expansion that we were doing originally in Q has broken down. All these terms are equally important. But if you add them all up, you get this dashed line, this dotted line, sorry, which is then approximated reasonably well by this dashed, this is this Gaussian asymptotic form that we talked about earlier. There's a slight offset, which can also be understood and corrected for, but that's a technical detail, really, that in practice doesn't really matter. So this is kind of nice. So we have control over this in a simplified form as well. So my colleague Tongyan's group has recently estimated the effect of anharmonic corrections in here, and so show that they're not qualitatively altered in this picture. So like 10-20% corrections to this story. And so here is a final answer then. So this is this plot I have to always be very careful about explaining. This is not a limit plot, and it's not a projected sensitivity plot. So what you're seeing here is just a benchmark cross-section calculation. So in other words, what I did is I fixed the rate to 3 events per kilogram year, right? This does not mean that the experimental collaborations will be able to achieve 3 events per kilogram a year. That's extremely optimistic. However, historically, this is just what, among theorists, this is the benchmark point that we have agreed on and that we use to benchmark our calculations against each other. So in other words, you should not take the y-axis very seriously here and just look at the qualitative features. So what you're seeing, if you have a very low threshold at low energies here in red, you're in the single phonon regime here around 0.1 MeV. Then if you move towards an MeV and higher, this sort of region here, the multi-phonon expansion starts mattering. And then finally, at high momentum, the individual high dark matter mass, sorry, the nuclear recoil calculation starts applying again. And we can do this calculation for arbitrary thresholds, as you see, but the different colorful lines. And so this is the first full calculation all the way from like single phonons to the full nuclear recoil that you can just smoothly interpolate between all the dark matter masses. And so what we're currently doing with Stefania, Tongyan, Pankaj, and Bethany Suter, who's a Toshi student here in Berkeley. So we're working on generalizing the story towards spin-dependent scattering for dark matter. So let me tell you a little bit about that. So if you do spin-dependent scattering, there are 2 different cases that you can consider. So if you're lucky and you can find yourself a material where you can polarize the nuclear spins, which is a very difficult thing to do in general, for its very large magnetic fields. But if you can polarize the nuclear spins and they're all pointed in the same direction, the calculation is essentially identical to that of the sort of single phonon calculations that we did earlier on. Like you can just apply all the results that we had earlier and it will just work, except that the prefactor will be different. It will depend on the spin rather than on the atomic number of the crystal. So there's a bit of a form factor. And so this was done by Catherine's group, and that has to be the wrong year. No, actually that's fine, in 2009. Wait, that can't be right. That must be 2019. Sorry, yeah, I must have just archived that. Yes. Now, usually, your typical dark matter detector will not be spin polarized, right? It's polarized nuclear spins is very hard, and your spins will be like, added, just like randomly oriented. And so you might think that if I have a long wavelength scattering, each of these are just going to give a contribution of different sign, and they're going to all destructively interfere and average out to 0. So this is actually almost right, but not quite. In a sense, there's always one term that doesn't cancel. And so the term that doesn't cancel is exactly the term where the contribution of the atom itself, the autocorrelation function in some sense. So this is what you're seeing over here. This is the full schematically, this is the full answer, right? The same correlation function as earlier. However, now I added this sort of spin operators in here. So this is the spin of atom L and the spin of nucleus L prime. And so if they're just randomly oriented, this sum will average to 0, except the terms for which L and L prime are equal to each other. And so then this thing will just square to a positive definite number. And now I have the exact same correlation function that we already calculated earlier to get the high momentum limit. And so we can adapt these results and make a prediction. We don't need to compare that with constraints on these models with pseudoscalar mediators. So this was done by Romani and Woolley like in 2000. They mapped out these constraints. And so we're going to be mapping that on this plane over here. So these lines are different types of models that they considered back then. And they include things like collider bounds, BBM, and so forth. I'm not super optimistic that this will be of interest because I think the suppression that we're getting here is probably going to be severe enough that most of these models you won't have any realistic direct detection reach. But, you know, it's something that we should just calculate because we can and just check that this is indeed true. And even if it doesn't, you know, give you anything promising, that's still relevant information for the experimental collaborations. All right. So finally, on the scattering side, maybe you know you're working on a model or you're an experimentalist who's interested in these things. These calculations are somewhat technical. We don't necessarily want to redo them, so we wrote a code that does all these things. It does also a bunch of things that I didn't talk about today. We have done electron recoils, Migdal effect, and we did some certain absorption processes as well. It's Python 3. It comes with some Jupyter notebooks and so forth. And the only thing you need is sort of standard Python packages and then Vegas. There's a little bit of multi-color integration in there. It works with lookup tables, so there's no DFT codes that you need to install. So they're all the results are supplied with the code. All right. So now this brings me to my dark matter, my background story. However, if I'm not wrong, I think we're sort of at the hour. So I propose that maybe I go to the conclusions, and then if anyone wants to discuss what we're doing with backgrounds, I can stick around and we can talk about it. But I don't want to leave people here who might have places to be, such as, for instance, lunch. The short story here is that we are working on trying to understand the role of crystal defects and whether or not they can source spurious dark matter signals. But let me just skip past this and get you go to the conclusions, and then we can talk about it more if anyone wants to hear about it. Okay. So yeah, so for the next generation of direct detection experiments, the sort of billiard ball paradigm that we've had for many years is no longer adequate, right? And the reason is that the de Broglie wavelength is long enough now that you see the sort of macroscopic or like at least mesoscopic structure of your crystal. You see the individual cells, you see electronic wave functions and so forth. And so we need to calculate rates with electrons and phonons, and that including effective effects like coherence, screening, and so forth. And we're pretty good at this now. There's many groups doing this. And specifically on our end, we managed to compute the dark matter phonon scatter into all orders now, which is very nice. We've also done dark matter electron scattering. We were the first group to include screening correctly. We computed the Migdal effect in semiconductors. And as I mentioned, we're working on the spin dynamic calculation now. So all these calculations are, as we do them, they get added to our public package. So we are working on this crystal defects. So just one issue that you worry about are Frankel pairs. So I didn't discuss this because of lack of time, but basically Frankel pair is when, you know, an atom got knocked out and is in the wrong place. And so you have a hole and an interstitial atom somewhere. And if they find each other and they annihilate, they produce phonons. And if that happens during your dark matter run, you might think that you saw dark matter, but really what you saw is the crystal healing itself. And you really don't want that. So we're trying to calculate what the rate for that process is. Hydrogen in particular is a problem because if you have hydrogen in your crystal, it's much more mobile than the sort of bigger silicon or germanium atoms. And you also might a priori worry about radiogenic defects. So a cosmic ray came in, it made a defect in the crystal, and 3 days later, this defect relaxes and gives you some phonons, and it looks like an event. Again, here we are working on estimating this, and we think that this is probably okay in the right conditions, but you definitely want to be in a mine to try to mitigate this effect as much as possible. All right. With that, I will just open the floor for questions, and then we can.
Yeah. Thank you very much, Simon, for a very interesting talk. So we already had many questions during the talk, but I'm sure there are more. And Kieran already raised his hand. Kieran, please.
Yeah, thanks for the talk. I just wanted to know if you could comment at all on the possibilities for sort of finding or engineering like materials with like really anisotropic responses that you could maybe do directional sensitivity or daily modulations in the context of dark matter. Is this? I know there's some papers on this, but I wondered if there's been more developments.
Yeah, no, that's an excellent question. So you can indeed do that, right? So what Kieran is referring to is that in the single phonon regime, let's see, can we go back efficiently enough? No, probably not. Let me just go back to the relevant slides, which I believe is this one. Right, so this is, again, sapphire is a very anisotropic crystal. And so you see here, these are various directions in the Brillouin zone. You see this thing is a mess, like it looks different in different directions. And so specifically this phonon mode that you might see, this phonon mode over here has a certain angle to it, right? And that means that the rate at which you excite this thing depends on the angle at which the dark matter came in with the crystal. So you get a nice daily modulation. Now, the unfortunate reality is that this only works for single phonon excitations, essentially, because, the only way the dark matter sees the extended structure of the crystal is by having a relatively long wavelength. So it can see multiple lattice cells at once. Once it starts to have shorter and shorter wavelengths, it starts losing knowledge of the extended properties of the crystal. And so for dark matter heavier than a few MeV, the amplitude of this daily modulation is going down very sharply. Now, to answer your actual question, so there has been quite a bit of work by Knapen's group in particular to try to find new materials with different anisotropies. And mainly, you can get some slightly larger amplitudes in some cases, but the main interesting thing is that each material that you design will have a very different modulation pattern. And so that's nice because if you were to see a signal, you just build several materials and you can predict based on one material what the response should be in the others, and you can correlate them and you can extract a lot of information. But it only works if the dark matter is between 10 keV and 1 eV in mass range, roughly. If it's heavier than that, unfortunately, just like with regular detection, you start losing this information because the wavelength is not long enough.
Okay, so there's another question by Jojo.
Yes, so all of this was thought for dye detection. I was wondering if it's possible to do this kind of computations also for in the context of crystals inside a white dwarf.
Yes. In principle, yes. However, of course, it's slightly different because you have to take into account relativistic effects, right? But in principle, so let me put it this way: like the first calculations that were done by Knapen's group before I got into this was where they did this for superconductors, right? Electronic excitation in superconductors, which is basically just a Fermi degenerate medium, and that's it. Mm-hmm. So those calculations, modular relativistic effects, you can immediately apply to a white dwarf. It's the same physics essentially, just a polyblock medium, except that now the Fermi surface is much higher, right? And you could certainly carry out calculations like this, yes. And I think some work has been done. There's been some work done on neutron stars because there was this story at some point about neutron star heating, right? If you have dark matter scatter, heats up the neutron star by Joe Bramante and collaborated with them. I think they did some calculations like this. Yes, but yes, you can certainly do that.
further questions? Any in the room? No? Let me ask you one more question on that. So you mentioned the background, so we skipped over them. So what's actually the dominant background in those experiments? What's the...
Let me show you. It's not fully known, but I can show you what they're currently fighting. I can show you what currently the dominant background is. Let's see. Yeah, so this is super CDMS and crest. So you see, they see a huge amount of noise at still relatively high energies compared to what I talked about, 100 dB or so. And so what this is characterized by its only phonon, so you don't see any electrons. And curiously, it decays off with time. So like if you start your experiment, you wait, like this background starts going down. Then if you heat up your experiment, you cool it back down, it resets and it starts again going down. So what they think this is microscopic cracks in the crystal that once you cool it down, there's thermal stress because the thermal expansion coefficients between the surfaces of the individual materials are glued to each other is not exactly the same. And so that you get stress, and once that cracks, it gives you, a burst of phonons at once. And so they were recently able to prove this because they built two identical detectors, one which they sort of suspended, they wire bonded, and the other one they sort of glued down with some epoxy glue. And so they found in here that the one with the glue had like a few orders of magnitude more background events than the one without the glue. So that suggests that the glue is really subject to thermal stress and injected phonons at random times. So this is the main background they're currently fighting. But they have some interesting designs to go around this because they think that it's mostly at the various interfaces here. And so by looking at coincidences between individual sensors, they can try to reject as much as possible. But this is currently what they're fighting. And then once they remove this one, the next background will pop up and we'll see what it is. But there's definitely going to be one below this as a document.
Okay, thanks.
So just a final one maybe. So out of curiosity, has there been any resolution to some of these low energy excesses that were discussed in the excesses workshop or something?
Yeah, so this is one of them, right? So this is a phonon excess. So the thought is that this is indeed these microfractures. There's another excess which is in the electron, in the electron experiment, they see way more single electron and double electron events than they thought they would. Especially if you look at the recent Dominic paper, they see a lot of background. That one, as far as I'm aware, is not yet understood. So here they think they're on their way to understanding the movie, as is sort of evidenced by this paper that I wrote and this plot here on the right side. But yeah, it's still a work in progress. But there is progress being made on the phonon side. On the electron side, I think it's still a bit of a mystery.
Okay. All right. Thanks. Yep.
Okay, so I think it's time to thank